Well, last time we proved that if m and n, if d divides m and d divides n, then d divides the sum as well. So what about if we did a times m? So let's take this off. If d divides m, then d divides a times m for any a in the natural numbers. So proof, what do we know again? Oh, I just worked it off. D divides m means d equals, no, m equals d times k, the sum k in the natural numbers. Let's call this one k1 again. So what does am equal? Then am equals, well, this is m, right? So it's a times d times k1. But if we rearrange that, that's just the same as d times a k1, right? So if we call this part k, then am equals dk. And k is certainly a natural number, because a times k1 must be a natural number. So we're done, right? Because we've got am in the form d times k. So that means that d divides am. So d divides am. So we're done. So that's the proof that if d divides m, then d divides any multiple of m. So this is a start about understanding divisibility. And one thing we can now do is we can very precisely define the notion of highest common factor or greatest common divisor. So let's get rid of all of this. And make a definition. So we're going to start with A and B, which are both in the natural numbers. So we're going to define the highest common factor or greatest common divisor. The greatest common divisor or highest common factor of A and B. Well, it's some number which is a divisor of both of those things. So it's got to divide both of them, and it's got to be the biggest among all things that divide it. Okay. So the greatest common divisor of A and B is some number, is any number h in the natural numbers satisfying two things, such that, first of all, h has to divide both A and B. H has to divide A and h has to divide B. And secondly, we've got to say it is the biggest among all the other divisors. So you might want to say, for all other divisors, h is bigger than it, but it turns out that if h is the biggest one, h isn't just bigger than all the other ones, it's actually going to be a multiple of all the other ones. So here we're going to say, if we have another divisor, so this one says h is a common divisor. So now I'm going to say, suppose we have some other common divisor. So if D also divides A and B, then in fact D divides the highest one. So this says that H is the highest among all common divisors. So this is the definition of highest common factor. And two numbers, well, their highest common factor might be 1, right? In the worst case scenario, the biggest number that divides both of them could be 1, right? But in other cases, it could be A or actually B. So, for example, if A actually divides B, then the highest common factor of A and B, which I might write like this, if A actually divides B, then that's going to be the highest common factor. So let's have some examples. Perhaps I'll put some examples down here. I'm sure you've fiddled around with this kind of thing before. For example, the highest common factor of 6 and 10, well, what's the biggest number that divides both of them? It's going to be 2. What about the highest common factor of 18 and 24? What's that going to be? Well, it's probably going to be 6, isn't it? Because 6 is the biggest number that goes into both of those. What about the highest common factor of 20 and 25? Well, that's clearly going to be 5. And the highest common factor of, let's see, 10 and 21, that's going to be 1. So you might say to yourself, how do we find highest common factors in general? Is there a good way of finding highest common factors? Well, in fact, there is an algorithm for finding highest common factors. What's an algorithm? It's kind of a method where you can just chug your way through without really having to think about it. It tells you what steps to take all the time, and then out pops the highest common factor at the end. And that's called Euclid's algorithm, and that's what we'll be doing very soon.